Okay, let's just review what we were talking about at the end of yesterday's class and finish it up. So we were talking about distance and displacement. And distance is the length of the path that an object travels, and it's a scalar. I'm sorry, problem when I try to zoom in. And displacement is a vector. It's how far you are from where you began and in what direction. So for example, if you started at some spot and then you walked, I don't know, let's say this is 6 meters east, and then you turned and you walked 4 meters north, and then you turned and you walked another 6 meters, but this time west, and then you turned, whoops, imagine that straight down, would you? And you walked 8 meters south. Okay, your distance would be 6 plus 4, which is 10, plus another 6 is 16, plus 8 would be 24 meters. That's your distance. What is the length of the whole path that you followed? Your displacement would be from where you started, which was right here, at this spot, to where you ended, which is down here. So your displacement would just be 4 meters south, because all the rest would cancel out. Okay, so if you've only traveled in one direction, like in this first little piece, your distance and your displacement would be the same. But as soon, or the size of it, as soon as you change direction, your distance, the size of your distance and the size of your displacement will no longer be equal. Okay, so that's distance and displacement. They are both delta d's, but distance is just delta d and displacement is delta d with the arrow over the top. You'll often also see vectors in a textbook written as bold instead of the arrow. So like the bolded one will be the vector and the non-bolded will be the scalar. But on the classroom board, it's really hard for me to do bold, so I just put the arrow over the top. Then we talked about speed and velocity. Speed is the scalar, and velocity is the vector. Speed is just how much distance you traveled in a certain period of time. So it's distance over time. Whereas velocity is your displacement over time. Now, hopefully, if you were in class yesterday and were there and we talked about this, you should be able to see that your speed is actually going to be more accurate for what you've done. So you take an athlete who's running the field or the court or skating or on the rink, their displacement is going to be much tinier because at the end of the game, they're going to end up not very far from where they started. Or if you're a track runner and you're going around the track a few times, you're going to end up back where you started, which means your displacement will be tiny or will be zero, which means your velocity is going to be minuscule or zero. Whereas in reality, your distance might be 4 kilometers, 5 kilometers in the course of the game, right? And so your speed would be a much more accurate reading of how fast you were going. Your velocity will be accurate as long as you're running in a straight line path. But as soon as you change direction, then this displacement is not really how far you went anymore, and it's going to be misleading. Okay? If you run at a constant speed, if you don't change your speed at all or a constant velocity, then we often we say it's uniform motion. And if it's constant speed, then it means your average speed isn't changing. And so we call this VAV, and for velocity, it's an arrowhead. So for speed, it will be VAV without an arrowhead equals delta D over delta T, no arrowheads, that's speed. For velocity, V average arrowhead is equal to delta D arrowhead over delta T. So for speed, it's distance, all scalars, velocity, displacement, vectors. Okay? And we talk about average speed because imagine if you are running a race or you are playing in a sport, you're not going to be going the same speed every second all along the way, right? You're going to speed up, maybe you're going to get tired, you're going to slow down. So this is telling us the average of the whole thing. Like, so however far you went over that period of time gives us an average of your speed. It takes into account the slowing down and the speeding up. Okay? These two, again, will only be the same size if you haven't changed direction. Okay? Now, usually when we talk about vectors, we need to define directions as positive or negative. So, as a universal standard, okay, so universally, most people in the world would say that we would define positive directions, okay, so positive directions we usually consider to be up, right, north, and east. So if you're doing a question that has objects with two different directions, then we would call, if it was up and down, we'd call up positive, down negative. If it was right and left, we'd call right positive, left negative. Okay, so the negative ones are down, left, south, and west. And this just comes into play when we go to put vectors together, which will be the next video. We'll put vectors together. Okay? So up here I had said if you were traveling at a constant speed, it's called uniform motion. There's really two types of motion. One is uniform motion, so the speed is constant, and the other is called accelerated motion. Okay? And for accelerated motion, it means the speed is not constant. The speed is changing. Okay? Now, the speed or the velocity can change in several ways. Most people, the unphysicsed among us, when they hear the word acceleration, they automatically think it means speeding up. And it can, but it doesn't just mean that. An object can also accelerate by slowing down. Because really acceleration means there's a change in velocity. Okay? Not in speed. Acceleration is a vector, so it's dependent on the velocity. So acceleration is a change in velocity. So you could change your velocity by speeding up. You can change it by slowing down. And here's the one that most people don't get. You could also change it by changing direction. Because velocity, acceleration is dependent on velocity, and velocity is a vector. So I could be walking around a classroom going 2 meters per second. First I would be going 2 meters per second east, but then when I turn, I now could be still traveling 2 meters per second, but now going south, and then turn again, and then now I'd be going west, and turn again, I'd now be going north. But if the whole time I'm going 2 meters per second, the unphysicsed among us would think I wasn't accelerating, but I really am because I'm changing direction. I think from grade 10, you know that the equation for acceleration is equal to the final velocity minus the initial velocity over time. Okay? It is a vector. It'll be measured in meters per second over seconds, which ends up being meters per second squared. And that's that flip and multiply thing, right? Because you're dividing by seconds, so that's the same as meters per second times seconds over 1, which gives us meters per second squared. And you do need to put a direction on. Okay, so because it can be speeding up or slowing down. If you end up getting a negative acceleration in a problem, it means the object's slowing down. The acceleration is in the opposite direction of motion. Okay, next video I'll go over your homework and then we'll talk about adding vectors.